Hello, this is Matteo. In this talk, I introduce sensor-guided optical flow. Optical flow estimation consists into finding the 2D motion field connecting pixels in two images. This latter usually acquired at consecutive time frames. In this example, we can notice how the car moves in top left direction, while the rest of the scene moves right, as a consequence of the camera moving forward on the road. Deep neural networks represent the state-of-the-art to tackle this problem. However, a number of challenges still threaten flow networks. Among them, the presence of shadows apparently moving with the objects themselves, or poor illumination conditions rarely observed by the network during training. In this paper, we propose guided optical flow, a paradigm designed to improve the accuracy of flow networks. Our framework assumes the availability of flow hints obtained from external sources. Given the correlation scores computed between pixels by most deep networks, we use the flow values suggested by the hints to build a modulating function centered on them and to pick the correlation scores corresponding to such hinted flows. To run our experiments, we select Raft. Specifically, we implement QRaft, a variant of such a network that computes correlation scores at quarter resolution in order to increase the effectiveness of the guidance. In early experiments, we source hints by applying random noise on values sampled from the ground truth. We train both Raft and QRaft with and without guidance on a variety of datasets and evaluate on Sintel, Middlebury, and Kitty. When training on a simple dataset such as flying chairs, guided flow always improves the performance of both Raft and QRaft. When training on more challenging datasets such as flying things, Sintel, or Kitty, the guidance is often harmful for Raft, while it always allows QRaft to sensibly improve its accuracy. Although this evaluation shows the potential of the guided flow framework, we need a strategy to obtain hints in the case of a real application. A possibility consists into making use of a depth sensor, for instance a LiDAR, and thus implement a sensor-guided optical flow pipeline. Given two frames and their depth, we compute the relative pose between the two. Then, for each pixel in the first frame, we use pose and depth to map it on the second frame and obtain its new coordinates. Finally, flow hints are obtained as the difference between coordinates on the two images. As we can notice, this approach allows to obtain very accurate hints encoding camera ego motion. However, it cannot effectively model the flow for pixels belonging to independently moving objects, resulting in completely unreliable hints. We can overcome this limitation by leveraging a traditional flow algorithm, such as Rick flow, to recover correct values for pixels belonging to moving objects. Then, we can combine the two sources, for instance by running mask-RCNN to detect objects, and select hints from LiDAR or Rick flow accordingly. This allows to obtain accurate hints on both moving objects and static regions. Our experiments show that QRaft, trained either on synthetic or real data, can always leverage the guidance provided by our pipeline to improve its accuracy. In this example, we show that QRaft is fooled by shadows when trained on Sintel. The guidance softens this effect, as well as it improves some details, such as the pool behind the car. Finally, we test our framework on images and low-resolution depth acquired by a mobile phone. We can notice how the original Raft is fooled again on these images by the tortoise shadow, while guided QRaft is robust to this effect. If you want to know more about this work, please join us at poster session 6. Meanwhile, you can reach from here our paper, supplementary material, and source code. Thank you.